about MPU. So MPU usage, and this is a memory protection unit. If you see, the CPU has the ALU, the registers, and then the load store unit. Basically, this interfaces to the memory. Okay. Now, the MPU is one of the things that sits between this and the memory. In fact, we may have cache also, cache controller and memory. This path is where if you chose to configure an MPU, it sits in between the LSU and the actual memory or the cache memory. So basically, it traps all memory transactions with only one goal, basically to check for access permissions and some cache related. So one is for access control or protection. Second is for cache related behavior or policies. And third is for memory ordering or reordering. These are the three purposes for which the MPU is coming into the picture. So if you see the MPU register, so MPU basically divides the physical memory into regions. And in Cortex M, I think there are 8 regions. Okay, so for each region, there will be an entry. So region number, and then there are certain properties. One of them access related, it can be a read, write, etc. The other thing is shareable or not. And then the ordering related information. Okay, and what type of device it is, basically type. Now, memory in an ARM nomenclature, there is normal memory and there is device memory. Device memory and then some system memory address space. If you know the memory address space, the system memory. These types are having specific properties. For example, normal memory can be again code or data memory. And device memory basically is for IO peripherals, memory mapped peripherals. And system memory is internal address space for control purposes, including the NVIC registers, including the MPU registers, and so on. All the internal SysTick, for example, all these are residing in this address space. So those addresses, you can have entries in the MPU with the attributes, whether it is read-only, read-write, or shareable, etc. One more property is about the cache. What property, whether it is write through, you can configure it as write through or write back. Basically, when the cache has to be updated in the memory, what policy to use for this particular region. So these can be specific to the region. So the regions are, so this is one data structure. The region number is basically the index or offset into this table. And then you have 8 regions. So you can have 8 entries. The regions themselves will have the base address and the size. The base address is where in the whole memory address space where this particular region is starting. For example, you can say 0x0000 as base address and some 8 KB. It can be set aside for code, let's say. It can be text or code. And you can specify read, write for code, because you might want to do only read only for code, or you may want to update code, so you may want write access to the code, software update purposes, and so on. So these are the general features of the MPU. And why do you need this? So basically, if you remember, ARM has two modes of operation, that is privileged uh, and unprivileged mode. So unprivileged mode will be restricted from accessing the devices, for example, devices or system memory. It may be even restricted from accessing other unprivileged code or task or whatever process, etc. So privilege has totally access to everything, especially the sys memory, sys control memory, through which it can program. For example, the OS can program the whole memory map for. It can program the clock. It can program the address space or physical memory, physical memory, or it can program the interrupt vector offset base, etc. So everything is accessible for the reset handler or the operating system. So those basically, how do you know that a particular code has what privilege level? So we talked about that in the MCU class, that the program status register and program control register has the privilege bit. Basically, you can set this bit with a MSR or MRS instruction, then you get the right privilege level depending on what value is programmed in that bit. Now, when that happens, if you see this path, suppose a code which is unprivileged code is running, and it is trying to drive an write an address. That address, so its privilege level is known. So basically, current privilege level of the CPSR is taken. The MPU will check in the data, in the entry, that it is basically what kind of memory it is, normal memory or device memory. Suppose it is a device memory and it's an unprivileged code, then it will raise a trap or basically a fault. So basically, it is doing this with respect to the current privilege level, and it is looking at the table which is having the attributes, what type of memory it is, and depending on that, it allows or generates a fault. That's all it does from an access control point of view. Of course, the cache behavior and memory reordering are not, they are not actively done by the MPU, but there is an involvement of the MPU registers there. The cache controller will use that information for write back policy or write through policy. And the memory reordering logic, that's part of the pipeline management. Depending on, okay, basically what you're saying is this region of memory is external memory, so it may be slow, so it may require more cycles and so on. So it may be doing it out of turn. It may do a prefetch of that operand via that external memory. All that, for that purpose, the MPU is used. So when to use MPU, when not to use MPU, right? When not to use is easy. If you have a very simple application, okay, so where everything is application, there is no operating system, nothing. So you may want to use that. You don't have the overhead of programming, programming these tables and so on. And remember, in a multitasking system, with OS, these regions that we talked about, these regions or can be reprogrammed dynamically. That means on a per task basis or per process basis. Which means as part of the context switch, okay, if you're moving from task A to task B, you can change these values. That's an overhead. And if you want to protect A and B from each other, you may have different attributes for task A. For example, task A may be an IO task, and task B may be a computational task. So you may want to restrict the computational task from not accessing the IO and so on. So basically, you have to, when you switch context from one task to another, you have to reprogram some of them. So if you want to change that privilege. So this is an overhead. So you don't want to go through that overhead. You can have flat memory. But anyway, you need to have what is called default configuration memory map, which basically says everything is accessible to everything. So, for example, you would need at least one entry for the code that's mandated by the hardware. That you say this code is these are the attributes of this code. So you need at least one entry for the registers. So one region at least has to be configured. And normally you will configure the physical memory. Okay. So you would probably have one for RAM as well, and one for IO space as well. Now, when to use it, or what is the benefit of using that? I would say the most important thing is if you want to detect, say, stack overflows or buffer corruptions, etc., you can use this. For example, let's say you have a producer task and a consumer task. They exchange information by this. This allocates a buffer. Allocates, or it owns a buffer, and then puts the data, application data, and then sends it, passes that buffer handle to the consumer. This basically consumes that. Now, this can be having write access, and this can be having read-only access. That way, you are truly owning this. This task is truly owning this buffer, and this cannot modify that. If you have any buggy code here which tries to overwrite that or write on that buffer that was passed by the producer, it will generate a memory fault. So this is one use case. And you can have stack region, and you may have so you'll have the stack, and then maybe heap and global data, etc. regions. Now, when the stack overflows, it overflows into some critical data, and it may cause problems. So you may set up a guard region, and it's using the MPU. You can say any access by any code in the guard region should raise a fault. Then you can trap that fault. You can write the fault handler, and then you can debug why this is. It because of the stack size problem, or it is some you're not freeing that. You are basically doing a invalid stack access because something got corrupted and so on. So basically, it can be used for development time to protect or detect such issues. Another similar use case is, for example, you have a null pointer reference. Now, sometimes you can use the compiler to help with that. But if you imagine null pointer, suppose you have the address 0, whatever the RAM address, base address for that section, as defined by the linker and loader, you would set up some RAM region or data region, right? Data section segment. So at that point, if you put this memory map, sorry, for the MPU entry for that region, if any variable is trying to access that address, it's a null pointer reference. So it can generate a fault, and then you can look at the code dump and then see why it happened. So these are all typically use cases for debugging problematic things, runtime behavior like stack overflows, null point references, memory corruption, invalid access by consumer, etc. So these are all typical use cases for the MPU. Of course, if, for example, this safe RTOS is a version of free RTOS, it makes sure that MPU is mandatory. That way, it can detect all these problems which are problematic for any safety critical systems. So you can treat them as hooks using the hardware, MPU hardware, to capture these kind of issues. And you can do recovery action based on the nature of the application. So this is when you would use MPU. And of course, if you're using a high-level operating system like embedded Linux, it may use this for enforcing some of the OS versus application segregation for physical memory. Okay.
Thank you. This is excellent.
Okay. Next question. Again, a lot of questions.
Raghu, in case of virtual memory, right? So how do you, fill in the MPU registers or the data?
Great question. So basically, a virtual memory is a very different animal, right? So you have a memory management unit for that. So MPU is for physical memory. Now, the memory management unit also has these attributes. It can leverage the MPU. That basically this has both software, hardware, and the software. Basically, what happens is that you have the page tables, right? So this is dealing with the virtual memory is dealing with translating the virtual memory address to a page address and offset, right? Now, in the physical memory, once you have done that mapping, this page is in memory, in physical memory. Then you may want to again apply the restrictions of the MPU to protect this physical memory. So it can, so this is transparent to the MPU, whether it is by the application in physical memory or eventually it is accessing physical memory.
Yeah, okay.
Okay, so the virtual memory first gets translated to physical memory, and then these attributes are applicable for the physical memory.
Got it. Thanks, Raghu.
Okay. What is it? Yeah, there's a bunch of questions from Subhash.
Raghu?
Yes.
No, sorry. On this point, right? So MPU is on physical, MMU is on virtual. So if you look at an RTOS, like you mentioned, free RTOS or safe RTOS, right? It creates different tasks, right? So would because I haven't worked on like an MPU based system, I mostly work on embedded Linux, which has MMU. So how would you, so in a virtual memory system, each process will have its own page table, and that page table has the mapping and all the protection and everything defined for each page, right? In the MPU, when the task switch happens, does also MPU also have something like a page table, which defines, okay, what is the mapping for this particular task, or it is always fixed MPU setting for across all the tasks?
Yeah, so basically MPU region table is global. Okay. Now it is the responsibility of the OS or RTOS to switch, basically give the illusion of or to multiplex across tasks if it requires differential access between tasks, right, for the same memory region. So that is why, as part of the context switch, the RTOS context switch, it will reprogram the MPU registers for that same region. Okay, so if you see the task control block, it will have a copy of the MPU registers, which will be reprogrammed, and then as part of that particular task. So for each task, there will be one, as part of the task control block information, the MPU's register as snapshot for that when that task was running will be saved, and then a new task when it is being scheduled, it will be programmed from its its own TCB values. So basically, MPU is global. It is, for example, if you have an IO-centric task, you want to run it in a unrestricted way, you may have in its task control block a read, write access, and so on for a what you call the device. It's a device type memory. So, whereas for another task, which is an application task, computational task, you may deny that. So but that region, physical region of memory, which is basically the region is physical base address plus size. This is the key for the MPU region. So this region is defined by the base address and size. And of course, you can have overlapping regions and things like that. But there is no notion of task here in this. The notion of task is in the operating system. So the scheduler will have to manage this for different tasks differently.
So So global region table, is that a table in the hardware, or it's just we just need to let the hardware know where the region table is present in the physical memory?
No, it is part of MPU registers.
So you have to, every time you do a context switch, you need to look at your current task MPU table and program that into MPU registers.
Right. That's correct.
Okay.
Like you have FPU registers, just like you have FPU registers. Then you have CPU registers. Okay.
Yeah.
A context switch will save all of these.
Yeah. Okay. Because in the case of virtual memory, especially on ARM, like you just need to change the TTBR0 or TTBR1, right? You just have, because you don't need to program the register. You're only programming one register, which is pointing to the different page table. So the other question here is the context switch code, which is going to write that MPU registers from the task MPU data, that has to have a higher privilege than any other task, right? And no other task could actually program those MPU registers directly at their privilege level, right?
Yeah, so that need not be a task. It is a OS scheduler or a dispatcher which does that. So it is not a task in that sense. The task is a notion managed by the operating system, but yeah, this is privileged code. So from MPU point of view, you need to be a privileged user or privileged mode to access the MPU registers. Okay, so privileged mode can only access MPU registers. So as long as, so that's why if you see, here is the application, it is making some system call, which causes some scheduler happening. So it will go through an SVC interrupt, okay, with a parameter and service number. So there will be a jump table, okay, for that entry, and it may be like, let's say, signal OS signal post or pend, whatever. So this function is, so as part of entering this system call SVC, you were in unprivileged mode or lower privileged mode, unprivileged, and you are getting into a handler which is privileged mode. Okay. And then here you are basically invoking the service, which is like semaphore, posting a semaphore signal. As part of that, you are running in privilege mode, and you will probably call the OS scheduler somewhere here. And these are all running in privilege mode, so they can change the MPU registers.
Okay. Yeah, I just wanted to confirm because on a high level servers like the Linux, you would have this model, right? But I was just curious, like in the free RTOS also. So the task basically runs in unprivileged mode, and then if it needs OS attention via system call, or it will
Yes,
call and get an attention. Okay.
right.
And
Yeah,
your
that's
actual RTOS kernel, which is scheduler memory management, that runs in the privileged mode.
yes, exactly.
Okay. Okay. Yeah. Thank you.